Thickeners are ingredients that can increase the viscosity of cosmetics and over-the-counter drug, cosmetic products. They also improve stability, modify appearance and products' aesthetics, improve applicability, and modify the rheology of a product. Thickeners can also be used to build viscosity in suspensions and act as suspending agents, for example, in nail polish formulations. Viscosity-increasing agents are generally differentiated based on their effects on aqueous and non-aqueous systems. Agents for aqueous systems primarily increase the viscosity of the water phase, as seen in oil and water emulsions. Conversely, agents for non-aqueous systems primarily thicken the oil phase, as observed in water and oil emulsions in cosmetic products. Examples for water-based thickeners include gums, such as xanthan gum and guar gum, cellulose and its derivatives, such as hydroxyethyl cellulose, hydrophilic clays, such as hectorites, bentonites, and magnesium-aluminum silicates, polyethylene glycols, PGs, such as PG200, and synthetic polymers, such as carbomers, and also sodium chloride. Examples for non-water-based systems include waxes, such as carnauba wax, long-chain alcohols, such as cetyl alcohol, organoclays, fumed silica, synthetic polymers, and polyethylenes, among others. When selecting thickeners, several factors need consideration, including the intended use of the products, the surface of application, compatibility with other ingredients in the formula, pH levels, for instance. Certain thickeners like carbomers require an alkaline pH for optimal viscosity and are unsuitable for acidic environments, clarity, the presence of electrolytes, processing temperature. For instance, waxes require melting to mix with oils, making them unsuitable for products made without heating and shear forces during processing. Some ingredients like carbomer require shear for activation and optimal viscosity, while others like fumed silica may be sensitive to shearing. Before discussing xanthan gum, I will provide an explanation of some chemical concepts. Intramolecular hydrogen bonding. Imagine you have a molecule that looks like a chain. Within this molecule, there are certain atoms that like to hog electrons more than others. These atoms, like oxygen or nitrogen, pull electrons closer to themselves, leaving hydrogen atoms with a partial positive charge. Now, when a hydrogen atom with this partial positive charge gets close to one of these electron-hogging atoms within the same molecule, like oxygen or nitrogen, it can form a special kind of attraction called a hydrogen bond. This interaction within the same molecule is called intramolecular hydrogen bonding. Intermolecular hydrogen bonding. Now, let's say you have two of these molecules floating around. Just like before, some atoms in these molecules are electron hoggers, creating partial positive and negative charges. When one molecule gets close to another, the partial positive hydrogen atom in one molecule is attracted to the partial negative electron-hogging atom in the other molecule. This attraction between molecules, where hydrogen bonds form between different molecules, is called intermolecular hydrogen bonding. In a basic way, intermolecular happens within a single molecule where atoms within the same molecule form hydrogen bonds. Intermolecular happens between different molecules where atoms from different molecules form hydrogen bonds with each other. Hydrolysis is a chemical reaction in which a compound reacts with water, resulting in the breakdown of the compound into simpler substances. Hygroscopic refers to the ability of a substance to absorb and retain moisture from the surrounding environment. Hygroscopic substances have a strong affinity for water molecules, and they can attract and hold moisture even when exposed to air with relatively low humidity levels. A polysaccharide is a type of carbohydrate molecule composed of long chains of monosaccharide, simple sugar, units linked together through glycosidic bonds. These molecules can be linear or branched and vary in size from a few hundred to several thousand monosaccharide units. Polysaccharides serve various functions in living organisms and have diverse roles in nature. Natural gums are made up of several sugar units connected by the glycosidic bonds known as polysaccharides. Plants comprising vascular tissues produce gums as a defense mechanism against any injury. The gums produced are heteropolysaccharides, but upon hydrolysis, they are converted into monosaccharides such as mannose, xylose, arabinose, glucose, uranic acid, and galactose. These natural gums are extensively researched because they are biodegradable, biocompatible, and sustainable, and are often used in different industries. Polysaccharides are isolated from renewable sources and have non-toxic, biocompatible, biodegradable, and bioadhesive properties. These qualities account for their use in food, pharmaceutical, biomedical, and cosmetic applications. Among them, xanthan gum has attracted considerable interest in the past 2 decades due to its safety clearance by the U.S. FDA in 1969. Xanthan gum is a naturally occurring extracellular heteropolysaccharide and is a fermentation product of Xanthomatus campestris, which is an aerobic, gram-negative pathogen. Xanthan gum is a dry, yellow-white colored powder of high molecular weight exopolysaccharide. The hydroxy and carboxy polar groups of xanthan gum reconnoiter intermolecular and intermolecular hydrogen bonding interactions in aqueous solution. Due to high molecular weight and hydrogen bonding interactions, an aqueous solution of xanthan gum exhibits high intrinsic viscosity at low concentration and behaves like a pseudoplastic fluid. High viscous rheology and pH and salt-resistant properties of xanthan gum are satisfactory for use as thickening agent, suspending agent, and stabilizers for cosmetics. Xanthan gum is an anionic material and is not usually compatible with cationic surfactants, polymers, or preservatives as precipitation occurs. Anionic and amphoteric surfactants at concentrations above 15% weight per volume cause precipitation of xanthan gum from a solution. Xanthan gum is compatible with the most synthetic and natural viscosity-increasing agents. If it is to be combined with cellulose derivatives, then xanthan gum free of cellulase should be used to prevent depolymerization of the cellulose derivative. Xanthan gum is available in several different grades that have varying particle sizes. Fine mesh grades of xanthan gum are used in applications where high solubility is desirable since they dissolve rapidly in water. However, fine mesh grades disperse more slowly than coarse grades and are best used dry, blended with the other ingredients of a formulation. In general, it is preferable to dissolve xanthan gum in water first and then add the other ingredients of a formulation. Cellulose derivatives such as hydroxyethyl cellulose, methylcellulose, hydroxypropylcellulose, and carboxymethylcellulose, CMC, are being extensively used to produce films due to their suitable properties. Hydroxyethyl cellulose is a non-ionic, water-soluble polymer widely used in pharmaceutical formulations. It is primarily used as a thickening agent in topical formulations. The concentration of hydroxyethyl cellulose used in a formulation is dependent upon the solvent and the molecular weight of the grade. Hydroxyethyl cellulose is soluble in either hot or cold water, forming clear, smooth, uniform solutions. Practically insoluble in acetone, ethanol, 95%, ether, toluene, and most other organic solvents. In some polar organic solvents, such as the glycols, hydroxyethyl cellulose either swells or is partially soluble. Normally dispersing grades of hydroxyethyl cellulose require more careful handling to avoid agglomeration during dispersion. The water should be stirred vigorously. Hydroxyethyl cellulose can be used with a wide variety of water-soluble antimicrobial preservatives. However, sodium pentachlorophenate produces an immediate increase in viscosity when added to hydroxyethyl cellulose solutions. Increasing the temperature reduces the viscosity of aqueous hydroxyethyl cellulose solutions. However, on cooling, the original viscosity is restored. Solutions may be subjected to freeze, thawing, high-temperature storage, or boiling without precipitation or gelation occurring. Bentonite is a type of clay mineral primarily composed of montmorillonite, which is a soft, porous clay that forms as a result of the weathering of volcanic ash. It is named after the largest known deposit of bentonite, located in Fort Benton, Wyoming, USA. Bentonite clay is highly absorbent and has a range of applications across various industries, including cosmetics and pharmaceuticals. Bentonite is a naturally occurring hydrated aluminum silicate used primarily in the formulation of suspensions, gels, and solutions for topical cosmetic applications. It is also used to suspend powders in aqueous preparations and to prepare cream bases containing oil and water emulsifying agents. Bentonite is a crystalline, clay-like mineral and is available as an odorless, pale buff or cream to grayish-colored fine powder, which is free from grit. It consists of particles about 50 to 150 mm in size, along with numerous particles about 1 to 2 mm. Microscopic examination of samples stained with alcoholic methylene blue solution reveals strongly stained blue particles. Bentonite may have a slight earthy taste. Bentonite is hygroscopic, and sorption of atmospheric water should be avoided. Aqueous bentonite suspensions may be sterilized by autoclaving. The solid material may be sterilized by maintaining it at 1708 Celsius for 1 hour after drying at 1008 Celsius. Bentonite should be stored in an airtight container in a cool, dry place.